So this problem is a little bit more perhaps interesting or difficult to set up maybe, or just maybe a little more confusing, but we'll go through it. It's not that bad if you just keep everything straight. The question goes as follows. A right circular cylinder is inscribed in a sphere of radius r. So find the largest possible surface area of such a cylinder. All right, so what does this mean? We have a sphere, and there you go. Again, I don't have such a thing where I can like draw like a tube that like I did before. So you're just gonna have to picture this. So here's a sphere. This is a sphere of radius r. And so what do they mean when they say inscribed? Of course, they mean that they have a cylinder inside the sphere where the cylinder is as big as it can be, in the sense of it's always touching the sides of the sphere, right? So in essence, what I'm thinking of is a cylinder something like this. So let me just make that into there, right? So here's a cylinder inside this sphere. All right. Now the cylinder, though, it can be very thin or it can be very fat. But in any case, it's always touching the sides of the sphere. So wherever it is, wherever we drew it, we can always draw this radius to any point there on that circle, right? Because like so we could in fact cut this off and we would have the top of that circle, but we're of that sphere, of that cylinder, which is a circle. All right. I think I made it more complicated with my bad description. But you kind of get, it's like maybe like a bead or something where you would hollow out the center. But we're not actually hollowing out the whole center, we're just inscribing this cylinder. Okay, so now the question is, find the largest possible surface area of the cylinder. So we need to find the equation of the surface area of a cylinder, figure out how it's related to the r in this problem, and then maximize by taking the derivative. Okay, so that's the idea. So the first thing is surface area of a cylinder. So if you don't remember surface area of a cylinder, I'm just going to draw the cylinder over here, and then we'll figure out what the surface area of the cylinder is. Now the thing is, usually with a cylinder, right, we think about the height of the cylinder and the radius of the cylinder, right? So here's the height, and this is the radius of the cylinder. Usually we use an r, but I don't want to use an r here because r was already given to us in the problem as the radius of the sphere. So this is r, so I don't want to use r to be this. Because if I draw the radius of the sphere, the radius of the cylinder, like it's this length here, or same thing would be this length here, height would be here. So let me give this some other name. I'm going to name it A. Okay, so my radius of the, right here, radius of my cylinder, we're going to call it A. Height of the cylinder, we can call it h, and the radius of the sphere, which is a constant for the problem, we're going to call it r. That they told us to call it r. So that's an interesting point. I want to make it clear. So I gave these two variables a and h because we can change the size of the sphere, we can change the size of the cylinder inside the sphere by changing the proportions a and h, but we can't change the size of the sphere. So r is a constant. So I'm not going to take the derivative with respect to r. In the end, there's going to be an r in my answer, right? Because r is held constant throughout. Now for my cylinder, to do the surface area of a cylinder, how do we think about the surface area of a cylinder? So you can imagine a can, right? Let me find a can here. We have a can. Okay, here's a can. This can has no top. All right, I'm not going to open a can use a can to show you what we would do, right? So here's a can, here's our cylinder. So what do we want to find out? The surface area of the cylinder. So what we could do is we can pop up the top and pop off the bottom, and then we'll just have the sides, right? Because we're trying to think about the area of all of those things. So if I pop off the top and I pop off the bottom, I have the top and the bottom. Each of those is, of course, a circle, so its area is going to be pi a squared because the radius is a. And then what's left is the can around, right? So how do I figure what that is? What I can do is I can cut it, and look, I even have this right. Let's see if I can do it. I cut it, right? Cut it, and I unroll it. Let's see if it works. Yes, and I have a strip, right? I have a rectangle. So this rectangle is what happens when you cut and unroll the side of the can, of the cylinder. So here's my rectangle for cutting it and unrolling it. Now, it's very clear that the height, right, of the cylinder is one side here. But what's the other side? Well, it was a circle before I unrolled it. So the length here, the long length, is going to be the same as the circumference of one of those top and bottom circles. So that's going to be 2 pi a in my case, right? Because the radius of the cylinder is a. So this strip has this length that goes exactly from our circle. So that's the way to remember that. If you forget, I don't ever remember this formula. Who's going to remember this formula, right? So you're going to add up all these things. So the area of the side then, all right, I'll just write it here. Surface area is going to be area of 2 circles plus the area of the side. So the 2 circles, 2 times pi a squared, and then the area of the side is just going to be a rectangle, h times 2 pi a. 2 pi a h. So you can always figure out the surface area of your cylinder. You don't have to remember this. So who's going to remember that? In general, the way we figure out surface area of things, of 3-dimensional objects, is precisely this. We kind of explode them and find the area of the planes involved, the planar figures. So the only difference with this cylinder is that you gotta think about unrolling it. All right. So this is our surface area that we are going to maximize. We're going to maximize it. So now what? Now I have to figure out, all right, how do I get R involved? Because what I need, as we've seen before, I have 2 variables. I've got A and H, and I need to take it down to 1 variable so I can take the derivative. So what's the relationship between A and H? So here comes the thing that it's inscribed in this sphere. If I go back to my sphere picture, I can see there's a triangle here, right? So let me pull that triangle out a little bit better so we can see it. R is the radius of the sphere, A is the radius of the cylinder, and H is the whole height of the cylinder, but this triangle is on the top, so this would be H over 2. So Pythagorean theorem can give me the relationship between these 3 things, right? So I've got A squared plus H over 2 squared equals R squared. So 4A squared plus H squared equals 4R squared. That looks pretty good. So what I want to do, it's going to be easiest probably to eliminate H, right? So if I solve this, I can get H being the square root of 4R squared minus 4A squared, or 2 times the square root of R squared minus A squared. Now remember, R is a constant. So I'm going to put this in there, and that's going to give me my, you know what? Well, I'll just write it here. You know what? I'm just gonna write it up here because I'm gonna need more space than this. So I'm gonna put this in here. So the 2 becomes a 4, and I'm gonna end up with 4 pi a times the square root of r squared minus a squared. Okay, so that's actually now that I've put h into my original surface area, I have this. I have it in terms of one variable, which is a, because r is constant. Now I'm going to take the derivative. I might get rid of that if I need more space. But I'm going to take the derivative. 4 pi a plus, now over here, we've got this situation, right? I have to use the quotient, the product rule. So, and then I have 4 pi times the square root of r squared minus a squared plus 4 pi a times 1/2 r squared minus a squared to the negative 1/2 times minus 2a. Okay, so these 2's cancel. Okay, so let me put it over here. I might as well use this space. Everything seems like it's got a 4 pi in it. Pull that out. I've got a plus square root of r squared minus a squared minus a squared over the square root of r squared minus a squared. Right? Because I get a minus from taking the derivative here of this minus 2a. So this is what I want to let equal 0. Ugh. Right? Kind of gross, right? But such is life. Oftentimes, by the way, so if it's a surface area, they can get kind of gross. It's just a lot of stuff. Okay, so the 4 pi, because now I've let this equal to 0, I'm going to drop my 4 pi. I'm just going to say, where is this thing equal to 0? In order for that to happen, I'm going to need a common denominator. So I'm going to make a common denominator for this expression here that I have in parentheses. The common denominator is going to be, oh, I screwed it up. Well, let me fix it. I lost this. Okay, so r squared minus a squared plus r squared minus a squared all over square root of r squared minus a squared equals 0. Okay. All right, obviously this has an issue when r is equal to a. What would r equal a be? R equal a would be my cylinder has no height, right? It's just like that plane right there, like that circle in the middle. So that's that's like the one limiting case. The other case, of course, would be so that would be like h equals 0, right? The other thing, you could have a being 0, right? In which case you just have like a stick down the middle. In both of those cases, you don't really have much surface area to talk about, right? So those are obviously going to be our limiting cases. Our maximum is going to be somewhere in the middle. The possible values of a go from 0 to r, right? Just visually, we can see that. All right, so I need to find the point in the middle where I'm going to have the maximum surface area. Okay. So I want to find where a times the square root of r squared minus a squared plus r squared minus 2a squared equals 0. Okay, so this is kind of a pain, right? Because I got that square root in there. I'm going to put this stuff on the other side. And then I have to square both sides, because how else am I going to work with this stupid square root, right? So algebra becomes a little bit of a thing here. So I square both sides. I'm going to get a squared times r squared minus a squared is equal to 2a squared minus r squared quantity squared. So this is a squared r squared minus a to the fourth is equal to 4a to the fourth minus 4a squared r squared plus r to the fourth. Okay, now remembering that r is a constant and a is our variable, we can actually kind of put this all together on one side and put it over, this stuff's over there, and we get 5a to the fourth minus 5a squared r squared plus r to the fourth equals 0. Okay, so this thing is essentially quadratic in a squared. What do I mean? I hate to introduce another variable, but there's too many variables, right? But you can think about if a squared is t, this would be 5t squared minus 5t r squared plus r to the fourth is equal to 0. You can do it that way if you want. So you can see it as a quadratic thing. Or you can just keep it with a, which is what I'm going to do, or a squared. So if I use the quadratic formula to solve for that, I'm actually solving this as a quadratic formula, but for a squared. So I'm thinking about this as a quadratic equation. So minus b plus minus the square root of b squared. Oh, shoot, I already forgot there. B is part of this. So actually, I should have written it this way. That would have made more sense. Sorry. No, I had it right. No, I didn't. Okay, it doesn't matter, right? But this whole thing is the constant, right? Because this is the, so if I wrote it as I had it, I'm not sure if I'm making this more difficult, worse. I don't know if it's worse or better with the t, but if you think about it with the t equals a squared, and then you see that you do have this t squared t and no t, so we can use this quadratic formula. So your b squared would be this, well, minus b, would that be that? So it would be 5r squared plus or minus now b squared, 25r squared, fourth minus 4ac, so 20r to the fourth over 2a, which is 10. All right, so what is that? 5r squared plus or minus, okay, this is root 5 r to the fourth, so root 5r squared over 10. Okay. You know what? Oh, I need that. No, I don't need that. What I need is this one. Okay, so let's look. Now I have two possible answers. So what is a then? My a is the square root of that, right? Because this is a squared, so I take the square root, and I only need the positive square root because a is a length, right? So what I end up with is the square root of that. And I can take the r squared out from both. Square root of that is r. So then I have r times the square root of 5 plus or minus root 5 over 10. That's not a great answer, but it's actually the right answer, okay? But there's an issue here, because 20 minutes of this video wasn't enough with this problem, right? There's an issue here. There's two answers here. It's 5 plus root 5 and 5 minus root 5. And I can't throw out one because it's negative, because they're both positive. So, and it doesn't really make sense graphically that there would be a maximum and a minimum. So there's a couple things you can do though. You could actually check which is the maximum or the minimum by checking the sign of S prime. But you wouldn't get the right answer. You wouldn't, and the reason is there's something subtle here. Why did I get two answers when I didn't really expect to get two answers? Like sometimes you can get two answers, but doesn't seem to be a reason in this particular problem that you would get two answers. So if you look back, you'll notice I said I need this one what did I do to this one to get this one? I squared both sides. So sometimes when you square both sides, you get a spurious answer. In other words, both of these two answers work in this equation once the sides are squared. But they don't both satisfy this equation, the one that we had before we squared both sides. Okay, so let's look at that. Let me just see which answer is the right answer, or if they both work. So we had this. That was our equation before we squared both sides. So now we want to double check. Check. Do both values of A work? And you know what? I'll let you do that on your own because I did do it, see? But it takes a little bit, all these square roots and stuff. It turns out for the first one, A equals R square root of 5 plus root 5 over 10 works. If I look at this equation, both sides equal R over the square root of 5. Or sorry, R squared over the square root of 5. But if I look at the other one, that's the 5 minus root 5 over 10, fails. So my left-hand side is equal to R squared over root 5, but my right-hand side ends up being minus R squared over root 5. So, of course, when you square both sides, these two are the same. So that's just that's what has happened. And in fact, it turns out that this is the right answer. Okay. And that is the maximum, which we can do. All right, this is the only critical point, in fact, because this doesn't even solve it. So this minus is a spurious answer. It's not a critical point. Okay, so we can see, let's see what the actual, so this is the n we want. And now we want to find the largest possible surface area, so we want to put this into there. So that's the last thing that we want to do. I didn't do that part yet, so let's see what that looks like. Yeah, I need this here. I might need more space. So I'm going to put A equals R square root of 5 plus root 5 over 10. And we're just going to evaluate what that makes us for, what that gives us for s. So 2 pi r squared times 5 plus root 5 over 10 plus 4 pi r square root times square root of r squared minus, oh, I think I did do some of this anyway. Well, it's very similar to what we did in the other one. That's squared that. Okay. So this is this guy. And then what happens here, I can pull out another r. Let me just do this over here. So I pull out the r that comes over here. Plus 4 pi r squared. Square root of 5 plus root 5 over 10. But what this then becomes is 1 minus 5 plus root 5 over 10 under the square root. So that's actually going to be, this square root is going to be 5 minus root 5 over 10. Okay, so these two, combine these, obviously the extra square roots go out. So what I end up with is 25 minus 5 over 100, right? So I 2/10, so 1/5. So this is 1 over the square root of 5. So whatever this is, let's see. I've got 2 pi. I bet we can come up with a nice answer here. 2 pi r squared in front of 5 plus root 5 over 10 plus 2. All right, come on. If I just leave this as 20 over 100, then, so I have a 10 square root of 20 over 100. I should have just done this before so you guys don't have to watch me. That's really, I apologize for being annoying. So 2 times 2 root 5 over 10. So 5 plus 5, root 5 over 10. Okay. So that's my answer. That's the final answer. The maximum surface area is 2 pi r squared times, well, how do I add this? 5 plus 5 root 5 over 10. Okay, so I could probably get rid of the 5s, right? And then rid of the 2, right? I get this and that, so I get pi r squared times 1 plus square root of 5. Oh, see, what a nice little answer. Oh, that's a mess. Yay! Units squared.